And thanks to IPAM for the invitation. I'm really enjoying this workshop. Contrary to many of the conferences we attend, there's a lot of variety and a lot of inspiration that comes from different fields and different contributions. And I find it really, really interesting. So I chose this sort of vague title because I have been working on different areas where equity and fairness had a role. So I didn't want to emphasize any of them, so I chose a sort of a more general title. So this morning, in fact, I added this last slide because I wanted to check how many papers I had with fairness or fair in the title. And I have 4 papers. And having fair or fairness in the title is a sufficient condition to care about fairness. So it is not necessary. So you may understand I'm a mathematician, first of all. And I mean, the topic is inside other papers, but at least in this, I was concerned about fairness. And you can see also that the application areas are different, all related to trafficking somehow. So traffic networks, facility location, collaboration in transportation. So I don't know if I will have the time to go through all of this, but I'll try to give you at least some ideas of these contributions in the direction of equity and fairness, which I consider synonymous. So, well, we have discussed a lot in these days about how to measure equity, what is equity, and how can we model a problem where equity is an issue. I work in mathematical programming, so to me, a main question is how can we enforce some degree of equity or fairness in optimization models? And we can do it, in fact, through the way we measure the quality of a solution. And we discussed a lot about this, but also through the way we define a solution, through the constraints, if you wish. So these are the 2 tools that we have to somehow incorporate, embed equity or fairness in an optimization model. So about the measure, we talked a lot, and I'm sorry to introduce a new measure nobody has mentioned yet. Well, already in other talks, we said average is a measure that we use often in optimization. We minimize the average cost, we maximize the average profit, right. And we all know that average is a criterion that doesn't measure variability at all. So if we have this kind of solution, we may minimize the average, but we see that there is a lot of sort of different outcomes for the different agents in this solution. So when in optimization, we realize we are not satisfied with the average, we use the min-max that we don't like much, because in optimization, this makes the solution much harder. So it's much easier to solve a problem where you minimize the average with respect to a problem where you minimize the maximum of a function. So if we have the mean average here, you may have this kind of solution. You have reduced the maximum outcome, but the average has increased. So on the left, you have a good average, but a very bad maximum. And on the right, you have a better maximum, but a much worse average. So none of the 2 in a way is good, because as we said already the first day, I think, during your talk maybe, John, the min-max just cares about the worst outcome, and the rest doesn't play a role. This can be corrected, in fact, with this objective function where you minimize the maximum plus a small parameter times the average. And then you have the mean average, the min-max, and this objective function takes care. So on the right, you have the same maximum but somehow you reduce also the average, right? So it is not yet ideal, but at least you do not have all the outcomes to go up to the maximum. That is what happens with the min-max. Okay. I come from a mathematics department. I went through a couple of computer science departments. I ended up in economics and business. And when I went there, nobody cared about traffic. Nobody cared about production. Nobody cared about anything of the things I had done. A lot cared about finance. So I went through journals, management science, operations research. Let's see if there is something. And I found papers, and I have a stream of papers on portfolio optimization. I never promoted that kind of research because I don't feel I'm an expert in finance. But I learned about conditional valued risk. Because conditional valued risk is a measure that has become very popular in finance in the last years because it satisfies a number of properties. And the idea, and companies use, banks, financial institutions use both the valued risk and the conditional valued risk. The valued risk is the maximum loss that you want to be exposed to, right? You don't want to have a loss higher than the valued risk, which is reasonable. And then you take the average of the loss above the valued risk. So in an optimization framework, you want to minimize the loss, the average loss, above the valued risk, which makes sense. You fix a threshold, and then you minimize the average loss. Fine? This comes from the famous paper by Rockefeller and Duryazev, 2020, I think. But I'm not a continuous person. I have very much worked in discrete optimization. So I understand the measure, but I work with tracks, goods, things, locations, all discrete. The concept of the conditional valued risk can be adapted to a non-stochastic discrete case where you minimize the average over a given percentage of the worst outcomes, right? So not the average, not the worst. You fix a percentage of the worst outcomes, and you optimize over this percentage. So you take care of a percentage of the worst outcomes at the end, right? Okay. So for example, in location, which is one of the areas where I have applied this concept, if you, for example, care about the 10% farthest customers, you may have this kind of distribution. So this is a solution. Given the values of the x variables, you can represent this solution through the frequency of the distances. So these are the customers that are farthest from any location that you have chosen. So these are the farthest customers, the customers that experience a worse service with respect to the solution that you have chosen. So the idea is that you fix the 10% and you minimize the average distance of these 10% customers, right? So not the worst, not the average, percentage. Of course, you have a parameter, which is the percentage, right? But you can play with it. So also what is interesting is that also in one of the talks of maybe the first day, we mentioned the convex combination of the average and the maximum, which is also a possibility. But there are solutions that you cannot find through the combination, the linear convex combination of the two functions, and that you find through this. And I find this much better because it controls the meaning of what you're doing. You take care of this percentage. So it's much clearer, much cleaner. So for example, in this example, there are 30 customers, most of them very close to A. I have different potential locations, C, B, A. And if I optimize the average distance, I end up with A, right? Because, of course, most of the customers are close to A, and that is the optimal solution. If I care about the maximum distance, this will be the solution, right? If instead I take the 10% percentage and I minimize the average distance of the 10% farthest customers, I will end up with B, right? So a compromise solution. It's a decision. The responsibility of the choice of beta is in the hands of the decision maker, but you can play with beta, and in general, it may be the case that you find a solution which is a good compromise. So for example, B, you see, the average has a value of the average which is much better than the others, but the maximum is high. If you choose the maximum is very low, but the average goes up. And if I choose B, I have a good compromise, both in terms of average and maximum value. Okay, this is good to know. I think this measure is not very popular because from the modeling point of view, it requires a bit of understanding. I think you can, I will show you now the model and I will comment on it. So this is what we do. And well, from time to time, you will see the papers where the results of what I'm presenting are contained. And I think all the papers, with few exceptions, are with colleagues from my department. So I will not give you the derivation of the model, but if you start from a mixed integer linear program, right, which is a classical mixed integer linear programming, the model where you minimize a given percentage of the worst outcomes is mixed integer, linear. So it's not much trouble to move from the average or the min-max to these different objective functions, okay? So without understanding how we got from here to here, which requires a bit of thinking, and we go through the dual also, but at the end, you can just apply the rule, right, if you wish. Okay, so linear, mixed integer linear, fine. Where, well, doesn't matter, as is the number of agents, the cost. When beta is equal to 1, the model is equivalent to the mean average. When beta is equal to 1 over the number of agents, it is equivalent to the min-max. So you can play, right, and control the number of unhappy customers, or customers or whatever the agent is.
Sorry, about the regularization you mentioned at the beginning, right,
yep.
with the lambda. There's sort of two mechanisms what could happen. One is that it actually changes the objective a little bit. The other possibility is that without the lambda term, you would be on an edge on the boundary. All the solutions are equally, and the lambda helps you select the one that helps with the other ones, right?
Yep.
So because of that second mechanism, that could still happen here as well, right? Yep. When you take the 10%. So wouldn't it still be helpful to introduce a small epsilon plus the rest as well?
Yes, of course, and we do.
And that's sort of an afterthought.
Yes.
Okay.
Yes, it does exactly the same. Right, thank you. So in this paper, we just compared the different location models. So the p-median minimizes the average, the p-center minimizes the maximum distance, and we also included and compared the new model where we minimize the average distance of the farthest customers. I want to mention this, heuristic because it's very simple. And since in these days I saw many presentations with mixed integer models. And sometimes, of course, mixed integer models create a computational problem. The exact solution cannot be found for large sizes. Heuristics, I believe that in many cases require a lot of effort and are very ad hoc. So for each problem, you have to design a new heuristic. And it's a lot of work, which I think sometimes is a waste in our community. We spend too much money and too much effort in improving heuristics. This is very simple. And in location problems, is extremely successful. We have the best solutions for a number of classical combinatorial problems on benchmark instances, location, knapsack, portfolio, a number of different. I'm just mentioning this paper because it is the first paper wherein we introduced this idea. And then we applied the idea on different problems. So the idea is, and for example, take location. Location problem, mixed integer, okay? You relax the integrality condition. You look at the solution of the linear relaxation. And there are variables that are positive and variables that are out of the basis, right? You choose the variables that have a positive value in the relaxation, and this is the kernel, the initial set of variables. And you solve the mixed integer program on a limited number of variables. And you find the solution. And then you add what I call here additional variables. You add some more variables, and you solve the mixed integer program. And sort of you play with this, right? So you just use a solver, Cplex, Gurobi, and you obtain amazing solutions. It's very good and very flexible. So we used this scheme, which is called the kernel search, and we applied it to different values of beta. Somehow we improved the scheme so that you take advantage of the solution that you have obtained with a certain beta to start with the next beta. So to find the different solutions for different values of beta without starting every time from scratch. Okay, cool. These are the typical results. We have solved the problems up to 1,000, 2,000 customers. It is not a problem. We can do it. And for example, here, just to give you an example, if you normalize the solution of the p-center to 100, you can see that the p-median, where we minimize the average, does much better, 28% less in terms of average distance, but the maximum distance is higher. And here you see these solutions are a very good compromise because they reduce the average distance by little and they increase the maximum distance by little. So it's nice to play, and you, of course, at the end, the results depend on the value of the parameter beta, but there's just one parameter that you can control through the solutions of the different for different values. Okay, so right now I'll go to traffic, and here both the way we measure a solution will play a role. But also the way we define a solution plays a role. And we heard also in other talks the user equilibrium, the system optimum. We know that the user equilibrium may end up creating congestion. System optimum gives a better solution in terms of total travel time, but we may have long paths for some of the drivers. So for example, if we think about our sat-navs, at the moment, I start in the morning, I have to drive, and not only I have to drive, many others have to drive at the same time, or around the same time. We will all be sent along the same path, right? This is the best path, we will all follow the same path. And shortly, we will end up in congested roads because of obvious reasons. Everybody goes to Milan. Well, not everybody, but a large percentage. Large percentage of the workers go to Milano for obvious reasons. So all are sent there. But there are other paths that are not that different in terms of length or traveling time. So it would be better to split the traffic flow, same origin, same destination, to split the flow into or more alternative paths. The main reason, however, why I showed this figure is to show you where Brescia is. Okay, so Venice is here. Honey knows.
I think I'd rather go to the lake than Milan.
Yes.
Thanks for showing us the nice region. But isn't it a little bit, if you take your route with Google Maps, you see where the congestion is at the moment. So if this one route is very congested, I would take the other one, right? So a little bit it is going more to this, that we don't all take the same path at the moment currently.
I think I experienced since I have worked on this for a number of years, when I drive, I always think about this. And it is not always true, Anita, because if you start in the morning and
when it looks good, maybe, yeah.
It looks good. It looks good. But when you start, and when you're here, you understand the traffic has changed, and we start with the expected arrival time, which is a certain time. After a while, the time increases because the traffic here increases. So the expected traveling time is a time-dependent value.
That is true, but the people who start 20 minutes after you or 10 minutes after you, they would maybe be guided
Not
to take the
always,
other
not
path.
always, because by the time I start here, right? I go here, there is not much traffic. The traffic starts here. So after 45 minutes, you may understand that there is congestion around here. And already many have taken this path. And there is no way to avoid the congestion. So, and also when there is an accident or anything, all are sent through the same path.
Yeah, true. But still, I would say with this online routing tools, it's better than before, where we just had the GPS or the map and just went through the shortest path, not knowing about everything. So.
Yeah, so I think there are situations and situations.
It's just a slight improvement.
But several times I experienced, I go to Milano quite often, and I start in the morning, and I look at the expected traveling time, arrival time, happy, and after a while, it becomes 10 minutes more, 10 minutes more, and I end up being late. And if I knew, I would have taken an alternative path.
I just wanted to lend some extra evidence to what you're saying, is I've experienced exactly that in LA this week. So
thank you.
You're welcome.
Not good news. Okay. So I think this is a problem because each sat-nav takes individual decisions without a forecast, which is very difficult to obtain, of course. And we might do something here now that we have the data, and we should forecast the traffic because every morning around this area there's traffic. So they should forecast and not just observe the traffic. In any case, this is the situation. So the idea is to, given a network and the OD metrics, assign a path to each user and to be equitable to users with the same origin and the same destination. We don't want users to feel that they have a path which is much worse than the path that is assigned to others with the same origin and the same destination. So we want to have similar paths for all the users who have the same origin and the same destination of the trip. This is not a new idea, and you know very well. In 25, a group of German colleagues, Ralf Möhring is the lead of the group, and they received an award for this paper. This paper is published in OR, and it was selected as best paper of the year or something. So what do we mean by paths are similar? Well, without going into the details, we can define a path inconvenience. We can choose a parameter that measures the maximum inconvenience that we allow, right? And inconvenience is the percentage difference between the free flow travel time of a path with respect to the free flow, the best path under free flow conditions. This is what is done in the paper by Jan et al. And this is what we have done as well. So we can build the eligible paths for each OD pair. And that is what they have done, right? So what they have done is to build up a model, Jan et al., that minimizes the total travel time on paths of bounded inconvenience. For each OD pair, all the paths that are considered have a limited inconvenience. So they're similar, right? So there is some degree of fairness. The model is nonlinear, and we have an exponential number of paths. And the paper, I read the paper multiple times. It received an award, but I have to say it is not clear. So the idea was fantastic because they were the first, and I think they deserve the award. But when you go through the paper, there are many details that you don't understand. So how they have generated the paths, so a lot is unclear. But still, the model has these features. So starting from that paper, we went on this kind of stream of works and generated a number of papers.
Sorry, I have a quick fundamental question. I mean, this is broader than the example of the traffic, right? But I'm still wondering about the example of the traffic that you gave, because if people commute, right, there's a sort of a repeated play of the game, and people gain information, what typically happens, and so on, and of course can use that to their advantage, right?
No, because if you go from Brescia to Milano, you have the highway. And the highway is always the first choice for everyone. And still, when I go from Brescia to Milano, I take the highway.
Right, but that could be done by just informing people, no, there's another road, right, one time and so on. You wouldn't need online tools. But the main point is with traffic is, right, how traffic is congested depends a lot on like, incidents, for example, right? Unpredictable events, right, that suddenly happen and can hugely affect what is sort of locally happening somewhere that is impossible to predict in advance, but can really, really be important, right? Highly relevant. So I'm wondering if this setup sort of the traffic is the right framework where one could sort of reliably apply these things. That's sort of what I'm wondering.
I agree, and I will show you later a project we are working on. Because from when we started working on this, I thought the real application should be online, not offline. So online, you have the problem, you have information, and you react. Yeah. And I hope we will get there. Okay, thank you. So, so the idea of Jan and co-authors, and also our first papers on this, was based on this scheme. So we generate the paths with limited inconvenience. We optimize, right? But then we can compute the real inconvenience ex post. Because here you generate the path on the basis of the free flow. But then the model tries to control the congestion. So only ex post you can calculate the real inconvenience. So, well, first of all, we use a heuristic here, which is a heuristic column generation mode, kind of heuristic of this kind. We generate new improving paths. We solve the restricted optimization problem, heuristic column generation. Again, this scheme is quite simple, right? And it works well. Of course, it requires some attention, but it works well. However, this is not the focus of my talk. I'm not talking about heuristics, but I say that if you have a mixed integer program, you can find a good heuristic solution without sort of spending too much in designing neighborhoods and stuff. So if you generate the path a priori ex ante, then there may be some paths that turn out to be more inconvenient than planned. And you may miss some good paths because in the generation, you do not consider the traffic. So what we have done, well, we are mathematical programmers. We just made the model more complicated. And we limit the inconvenience in the generation of the paths. We have plenty of variables that are binary, but since a long time, I'm not afraid of binary variables. I know how to handle through good heuristics. So I can do that. And well, this is just a kind of figure to show that this is the system optimum. This is the user equilibrium. These are two different ways to control the inconvenience of the path. It doesn't matter. What I want to show with this figure is that this is the maximum inconvenient, 5%, with respect to the best path. So with 5%, you already easily converge to the system optimum, right? So with the limited inconvenience, you can get to the system optimum, which is good, right? Then we were not happy with all this story. We get passionate about the topic. So travel time, arc congestion, maybe arc congestion is also a good measure. Why travel time? At the end of the day, we want to avoid congestion of the network. So let's look at the congestion. So we took the arc congestion index. We approximated the function, which is nonlinear, with a piecewise linear approximation. And we minimize, with this new model, a given percentage of the most congested arcs. So not the most congested arc, not the average, but a given percentage. So if you know that in the network there are 3 or 4 arcs that may be heavily congested, or you know that they are heavily congested, you can take that percentage and just include those arcs in the objective function. Okay, again, another model. This is linear. Fantastic. I like linear. If I can avoid binary variables, I'm happy. So this is linear. And for example, if I take this tiny example, if I minimize the average congestion is 27, whatever this is. The maximum is high. And if I take 20% of the worst, that in this case is just 1. This is the one that is heavily congested. I end up with a solution where the worst is very close to the average and not very far from this average, right? So there is something here that I think is interesting. And also for this model, we find the same kind of result, that with a limited inconvenience, around 5%, we converge to the best possible solution. Good, end of the story of the models. Now the application. I don't know if you have seen on TV, this Ponte Morandi, the Morandi Bridge in Genoa, that collapsed, right? And that created in Italy concerns, because this is one of many, many bridges, right? There's a problem of maintenance. The bridges were built over time, but many are very old. So if this has collapsed, what about the others? So there's a problem here. There were many people who died here. Surprisingly, some survived. The car crashed, a couple survived. However, many dead. So this was the starting point of a project that some colleagues from the civil engineering department in my university started working. The project is financed, supported by Regione Lombardia. And they have systems to monitor the situation of the bridge, right? So the movements, and they understand somehow they can measure the risk of the bridge. Brescia, in particular, and that's why they got the money to work on this project, Brescia is an area where we have many companies, industries in metal production of tools of different kinds in that, which means trucks are very heavy, right? So it is a problem. So the bridges are not a problem as long as we go through the bridges with our cars. But when we go across the bridges with very heavy loads, then it is a problem. And to make things worse, the trucks often are overloaded. They exceed, the load exceeds the capacity, right? Because of course it's additional cost too. So this is a particular bridge where my colleagues started working. And you see the number of vehicles, 35,000 vehicles per day per direction, right? So lots of traffic and lots of trucks. So my colleagues, well, not the civil engineering colleagues, but my colleagues in transportation engineering, transport engineering. This is called a WIM, weight in motion. I'm learning things I didn't know about. So they can weight the load, not the load, the overall weight of the truck. And they could measure the weight in 2 million plus vehicles sampled by this weight in motion system over a period of 5 months, many overloaded, okay? So it is a problem. So they designed this kind of solution where you have, this is the bridge, this is the entering, the main road, and you have also an entering, exiting road. Here they have the weight in motion device. So the idea is that the trucks come here, they're weighted, and there is a video management system where indications are given to the trucks where to go, if they can go across the bridge or if they have to leave their path and take a different exit to go here, right? And there is all the system here to handle this kind of. I learned, because now we have a team, because we received additional money from a big project in Italy, additional money to continue working on this project, and I'm working with them. So my civil engineers colleague, they have the system here to detect, to monitor the status of the bridge. My colleagues here, experts of the weight in motion systems, blah, blah, blah. And then the computer scientists and telecommunication colleagues, right? So there's a team. Okay. And surprisingly, they are interested in what we know. I was shocked. I thought I was doing research, pure research, so they're very interested. And now the idea that I'm working on with them is to get information about the trucks that come from different roads, and they want to cross the bridge. And the idea is to understand, first of all, that there are trucks, that they want to go across the bridge, and then we have to react. But when there is a problem on the bridge, and we send these trucks away, we should do it in a way that we do not create congestion in the network. So the idea is to optimize the distribution, the rerouting of the trucks so that we avoid congestion in the network. This is the overall idea. And of course, there are a number of problems. We are working on this project since almost a year. And this year was essentially spent in understanding each other. So what you do, what I do, what can be done. So can we assume that we can see the trucks coming from different roads and Yes, we can put cameras, and this is not a problem. How can we give information to the tracks? And here the privacy issue comes. So there are a number of issues that are not clear. We are working on the authorities. But the idea is that through the online version of not exactly the models that I have shown, but a variant of those models, we can reroute the traffic along alternative paths that are allowed to tracks. And also what I realized is that when you want data, we have data everywhere. When you want data, they're not available. When you have a clear idea of the data you want, and here, to simulate first, before implementing, we would like to simulate, and we will need the traffic flows of the tracks, of the heavy means, and this is not allowed, this is not available. So, how much time do I have?
Just 9 minutes.
Okay. So the problem is that we are struggling with the data, right? In any case, this is the direction where we are working. And yeah, there's a lot of work here, not only by my group, but also by other groups, in particular in defining a risk measure related to the breach. And now my colleagues are also interested in not only sort of avoiding the risk of the breach to collapse, but also to maintain the breach longer. So to somehow also reroute tracks if the breach is not going to collapse, but is not in good condition. So we try to maintain the breach for a longer period of time. Okay. So how we define a solution? And I want to mention here the collaboration, which is the other direction where I have done some work. Because we all know that in transportation, several of the customers may be inconveniently located for the companies, and this creates additional traffic. So how you make companies to work together to avoid this kind of additional traffic and additional cost. So this comes from an experience, a personal experience, because I was going to the airport of Milano Linate, and with a taxi. It was not a taxi, it was one of the companies with drivers, right? It was not Uber, because Uber was not allowed, is not allowed in Italy, it's illegal. But so during the trip, the driver received a call, and he asked me whether he could drop me before the airport, that another driver would have picked me up and brought to the airport, right? Well, what's that? I have my flight, right? I said, no worries. The driver is very close. There is no risk. We arrive and you immediately, okay. So I asked a number of information. He said, look, we are different companies, and we used to compete on sense, right, to attract customers. And we started exchanging time. So we drive for the other company if it is convenient, and they will drive for us if it is convenient in a different moment. So they work the same amount of time that they would have worked without the collaboration, but they reduce So that was the starting point. So we developed a model. If you have routes without collaboration, you may end up with the long trips, right? While if you think about this blue customer, it would be very easy for this company to serve it, and it is very inconvenient for this company. And of course, if we optimize the whole system and we minimize the total length of the routes, nobody will do it. Because the solution, this is part of many papers, it is mentioned in many papers, the large companies will do most of the job. right? So we have to impose that the collaboration is fair to everyone. And the idea of fairness is to control the amount of time that they exchange. In the optimization, we can control the time that is exchanged so that in one day or in a week, as we want, we can model the day or the week, the total amount of time or the total number of customers, here is the total number of customers, is the same. Same or within a certain bounds that you defined, right? And so you can build routes as fair as you want, and you can save a lot in terms of traveling time.
So I was just wondering if you impose that, would the larger companies lose incentive and choose to?
No, the small companies will not accept the collaboration. They're going to lose because since the large companies, for the large, it's more efficient for the large companies on average to serve additional customers because they have a big basis. For the small companies, it is not as advantageous. So the big companies tend to serve the customers of the small companies and not vice versa. So an imbalance arises that will make the collaboration fail in a very short time. So there must be some guarantee to, you can control through the model also the profit. You can include constraints, additional constraints if you want in the model. But I think these constraints are the most essential constraints because the companies want to work and to earn, to gain from the collaboration, right? And the savings are substantial, 20%. So 20% less traffic, 20%. And you can build a model that is constrained over one day or over a period of time. This can be done without any particular problem. This is done, for example, in a period of time, on 7 days. We tested the models on instances with data taken from a number of European cities. So these are for Berlin. And the idea is that there is an imbalance on day one, but when you get to the end of the week, you reduce the imbalances, right? So you may constrain the balance over one period or over a longer period of time, depends on you. So this will depend on the agreement that the company, what they like or what they don't like. Okay, that's it. I went through all the possibilities that I had in mind at the beginning. Thank you very much for your attention.